Hello and welcome back to Decision Analysis for Agricultural Development. I'm Cory Whitney, and this is part two on decision analysis, which we will talk about the theoretical background and some of the grandfathers of the approaches, and also give some more general overview about how these approaches are applied. Um, and give you a few more small projects to do. That is something to follow up and do practical application. Please, if you have any questions about all of this, be sure to follow up with us, with your colleagues and fellow participants in the Slack channels, or contact me through any of these contact methods. You can also follow, if you want to get more in-depth information, you can find out more from the GitHub account that I've mentioned here. And yeah, feel free to create any issues there. Let me know what's going on. Looking forward to sharing with you. So in this portion of the series, we'll talk about decision analysis. So application of decision analysis in the way that we use it really requires, first of all, holistic understanding. We have to build holistic models in order to support decisions. And for agricultural research, it makes sense to me to use this metaphor of the blind group of blind people who encounter for the first time an elephant. And the first who, the one who's at the front of the elephant here, the trunk, is saying it's an elephant. They're trying to describe this complex thing in the simplest of terms, according to what information they have, what knowledge they have. And they say, oh, it's a snake, or it's a brush, or it's a trunk, but none of them has a clear overview. Sometimes this can take disastrous forms where they really have no idea at all. This one's saying it's soft and mushy because he's encountered the poo of the elephant and thinks that is what makes up an elephant. And you can think about this using this metaphor. Think about someone who purely arrives at a smallholder's farm and says, oh, we just take soil samples and that's all we need to know. Or someone who says, oh, we just need to know about plant diversity, or we only need to know about this or that. They're very facultative, very specific field rather than taking a holistic perspective. So rather than critique all of those sciences, what I'm saying here is that in order to support a decision related to that complex system, we need to have some kind of a holistic understanding. This echoes the work of Alexis Carrel, who said every specialist, speaking here about medical sciences, was saying every specialist believes that he understands the entire human being, when in reality he only grasps a tiny part. You can see here even Alexis Carrel was a bit misguided in that the gender normative use of he here for the researcher. That's a bit of a side note. So decision analysis, if you look it up in Wikipedia, which I did to try to find something for a succinct definition for this presentation, decision analysis is a discipline comprising the philosophy, theory, methodology, and professional practice necessary to address important decisions in a formal manner. There it is, perfect. Just really succinct and clear. That's what decision analysis is. And there are two main questions that we really have to use. This is a piece by one of our collaborators, Keith Shepard, and his colleagues, including my boss, Ike Ludling, where they said the two main questions are really, what is the rational course of action based on our current state of knowledge, and which priority measurements could help us make better decisions? That's what we do with those complex models. And we generally take those complex models, as much as we know about the system, trying to be as holistic as possible, the different outcomes of the different possible outcomes or interactions given the decision states, and we apply stochastic modeling tools, that is, probabilistic modeling approaches, to run those mathematically and then generate those outcome distributions, which we talked about in the previous session. We're not the first people to do this, and agricultural research is not unique. In fact, it's rather rare in agricultural research, but quite common elsewhere. There are some great minds who have put this into practice. Ron Howard, we spoke about in past sessions. There are also others you may know. Daniel Kahneman, best-selling author of a number of books. There's Daphne Kohler and Jane Kim. Got Daniel Kahneman and a number of others. Norman Fenton has a big group. Doug Hubbard has spoken to our group a number of times, and he really promotes this a lot among business users. So lots of good minds in decision analysis. It's not ours. We didn't make it up. Can run these probabilistic scenarios with a Monte Carlo simulation. As I said, we use stochastic modeling approaches. So one of those that we commonly use in our group is a Monte Carlo simulation. Let me explain briefly what that is. So can we work with what we actually know rather than allegedly precise numbers that we aren't really sure about? That is, can we work with somehow expert knowledge and our general understanding instead of some empirical data that was gathered through who knows which kinds of processes and how those processes might have influenced the actual total data or the kind of perception that we get through the data. So can we use expert knowledge instead? The question here would just be more of a deterministic methodology. We would say, how much is A plus B if A is 1 and B is 3? I'll give you a second to think about that. If A is 1 and B is 3, then A plus B has a very clear value, right? It's a single value. But if if we assume a normal distribution, we say that A is between 0.5 and 1.5, and B is between 2.6 and 3.4. This seems absurd in some ways. It does seem like we're making this more complex than it needs to be. But when we're asking farmers, for example, to describe what they can expect for yield, or for sellers to tell us what they can expect for market prices in the next months or in the next years, or other factors that we have uncertainty about, this might be a more realistic kind of answer. And it might even be, my experience is that this is an answer that people are often more comfortable talking about, and they can be trained to do this accurately. That is to say, they can be trained to say that they can be right 9 times out of 10. That is, their distribution can contain the correct value when they say that they're 90% certain. So these are maybe even more realistic than going to the field, for example, go to the market and just look at the prices of bananas and assume that this value that we got now represents somehow the future state. So we can instead try to generate a distribution of uncertainty that is a distribution that we feel confident represents the different possible future states. And if we assume normality, again, in this case, normal distribution, and we're 90% certain that these values have this kind of distribution, then we can add them together. And what it does with the Monte Carlo simulation, this is a methodology for drawing distributions from those from A and B. It draws samples from those distributions, adds them together, and creates a new A plus B distribution. So this is our uncertainty about the addition of A plus B. We get a nice little distribution, and instead of saying it's definitely 4, instead we say that A plus B is somewhere between 1 and 7 with a lot of certainty around 4. Another method This is the decision analysis process as drawn by my boss, Eike Ludeling. Basically, we start with understanding a decision, and as you attempted in the last session, and as we discussed, defining a decision can be challenging in the first place. But once we have a decision, a clear decision with expected outcome and allocation of resources that needs support, something that we can support, a decision that we can apply this methodology to, then we run this participatory analysis and build this decision model, right? Where we run these probabilistic simulations. We can use any stochastic tool really for that. Monte Carlo and Bayesian networks are most common for us. We get a plausible range of outcomes. Based on this range of outcomes, we can either identify knowledge gaps and do supporting research to, again, plug new risks and uncertainties into our model, or if we find this plausible range of outcomes is overlapped in such a way that it's clear that we can make a decision support, then we can give some recommendations, and these development decisions can be made for better outcomes through the decisions. So basically what we're doing is we're doing science with fuzzy information. That's one trick. We're figuring out how systems work. That requires lots of expert inputs and real understanding of the system. We estimate our state of knowledge, and we apply something called the value of information, which I'll talk about in a future session. But the value of information helps us to understand which parts of the model are most important to follow up on in case there's any uncertainty, too much uncertainty in our decision support. And what we have in the end is an analysis strategy that's capable of addressing decision problems. What I'd like you to do now is think about some place where these mathematical approaches might be appropriate. And I would ask you to think more in terms of the Monte Carlo analysis. In the Monte Carlo, you'll remember that we took distributions of uncertainty rather than direct measurements. Since we're talking about future case, we can't travel to the future to take measurements, so we have to provide uncertainty about that future where these decisions have been implemented and these changes take place. So what I'd ask you to do is to think about your own research and provide 3 examples of uncertain values. That is, describe 3 variables or factors that have uncertainty. These variables should be important for some kind of a decision, so they should be relevant ideally to your research and be important to some kind of a decision, but have uncertain values. Uncertainty has to exist for these things. So give us 3 examples of values that you think might be appropriate for stochastic approaches or decision analysis approaches and in forecasting decision outcomes. You can share that in the Slack or any other way that you feel comfortable. I'm sure the rest of us will be happy to see what you come up with. And you can follow the next video in the same channel.